Today we will finish our discussion of carbonyl addition and substitution reactions finally and get on to actually our next carbonyl topic. Last time we were talking about ways to make new carbon-hydrogen bonds at the carbonyl, in other words, reduction. And one of the reagents we talked about to use for that was lithium aluminum hydride. There's the hydrogen source. And it's an addition to the carbonyl followed by a protonation of the tetrahedral intermediate. So last time I left you to think about some other reactions of lithium aluminum hydride with carbonyl containing functional groups. What would the products and mechanisms be? So let's talk about an ester first. I'm going to put a phenyl over here just because it'll be useful to differentiate what's going on here. So we're going to ask the same question if we take an ester and react it with lithium aluminum hydride followed by H3O plus, what are the products going to be? Figure that out in the same way we figure it out every time we ask this question. What is the mechanism? All right, so let's start with what do we do? Now remember the H3O plus, because this is this 1,2 notation, this means H3O plus, strong acid, not added until after we're done with the lithium aluminum hydride portion. So initially there's no H3O plus present. And also remember that when we go to the second step, that means that we assume stuff that we've added in the first step is gone, destroyed, doesn't matter, no longer available. So when you write this mechanism, we don't want to see lithium aluminum hydride, then H3O plus, then lithium aluminum hydride again, because the second time it's gone, it's not there. All right, so mechanism, how do we start this? We don't have a strong acid to protonate the carbonyl with. We do have a nucleophile. We talked about lithium aluminum hydride being a nucleophilic hydride source. So that's how we're going to start it. Take our ester. There's our AlH4 minus anion. The lithium has really nothing to do with this. So instead of ejecting H minus all by itself, this is not the Chichi-Bobbin reaction, so we can't have free H minus floating around. So what we're going to do is take this aluminum hydrogen bond and use those electrons to make a new carbon hydrogen bond. We've used sigma bonds to do this kind of thing before, and when we talked about Grignard reaction, when we talked about, we saw it a few times in electrophilic aromatic substitution. And this is driven by the aluminum getting rid of its negative charge. I shouldn't even have to say at this point. Eject the leaving group, right? Feed the cats or make coffee first. Remember that? You don't remember that? Let me remind you. Oh, now you remember. Feed the cats or make coffee? Feed the cats, eject the leaving group, right? Remember when I get up in the morning, I have two things I have to do: feed the cats, make the coffee. But if I don't feed the cats first, they're trying to trip me up and getting in my way, meow, 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 if I ignore them and make the coffee first. So I got to feed the cats first, get that task out of the way. Same thing here, intramolecular process first. What are my leaving group possibilities when we try to reform the carbonyl? Phenyl, that's never a leaving group. Hydride, hint, this is not the Chichi-Bobbin reaction. Hydride does not leave. That leaves us with OCH3 minus. Can that leave in this circumstance? Yes, tetrahedral attic with a negative charge on the oxygen, so the O minus can push out the O minus, and that takes us up to an aldehyde. And then a molecule of methoxide, our leaving group. So it's a substitution reaction. Are we done? Hint. If lithium aluminum hydride can react with an ester, if it is powerful enough to react with an ester, it's powerful, finish the sentence. Certainly powerful enough to add to an aldehyde. Aldehydes are much more susceptible to nucleophilic attack than esters. So the second, another AlH4 minus can come along and do the second addition. Now, I'm being a little bit simplistic here. In the actual mechanism, it may not be AlH4 minus, because as this mechanism goes on, if you write out the entire thing and think about it, what happens is the hydrogens on the aluminum get replaced by oxygens, O minus oxygen. So you might have at any given point aluminum with some number of hydrogens and some number of oxygens attached. And in reality, all 4 hydrogens from the AlH4 minus can actually get transferred to carbonyls. But we're going to just be simplistic about it and write AlH4 minus. So again, there's our second nucleophilic attack on the carbonyl. Takes us up to a tetrahedral intermediate. Negative charge in the oxygen. What do we try to do? Eject a leaving group. Benzene ring, no. Hydrogen hydride, no. Hydride, no. So what are we left to do? At this point, there's nothing else to do with the AlH4 minus. That's when we go to part 2, H3O plus. That's when this guy gets protonated. And the net result is that the carbonyl compound the ester gets converted to an alcohol. Now, the OCH3 minus that we get kicked out also gets protonated. So we end up with another alcohol. So the net effect is that the ester gets broken apart and the 2 portions, the carbonyl portion and the OR portion, both become alcohols. This works, so it works kind of with any ester. And we get 2 hydrogens added. This is very much like the Grignard plus ester case. Remember, we took an ester and reacted it with a Grignard. We got 1 addition, or 1 substitution followed by 1 addition. We asked a question there about stopping in the middle. Let's ask the same question here. It would be nice if we could take the ester to the aldehyde and stop here. Can we do that? No, because the aldehyde is more reactive than the ester. So as soon as any aldehyde is made, and it's in the reaction and competing with the ester to react with AlH4 minus, the aldehyde reacts quicker. So this is slower, this is faster. So you really just can't fish this out. There are other ways actually to convert esters to aldehydes, but using reagents that we're not going to talk about here. All right, I also asked you last time to think about 2 more related reactions. One of these was the reaction of a carboxylate, let's say this guy, with lithium aluminum hydride and then H3O plus in the second step. Yes, sir?
Where did you get the methanol in the final product there? Like
the methoxide that got kicked out here also gets protonated to make methanol.
Okay.
So what about a carboxylate? What will that do? Well, it turns out that it also makes alcohols. And you might say, wait a minute, shouldn't this be no reaction? Didn't we say that carboxylates are resistant to nucleophilic attack? They are for the most part. They are, as somebody once said, the Rome of carbonyl compounds. Resistant to almost all outside aggression. Here come the barbarian hordes. I forget who it was. My history of that portion of the world is pretty weak, so I forget who actually conquered Rome in the end. I know somebody once said, oh, it's the Mongols. Different continent. Actually, I think it was greed that conquered Rome. But anyways, this is the one nucleophile that is powerful enough, the only nucleophile we have talked about, which is powerful enough to attack the carbonyl. I'll let you work out the mechanism. Good exercise for you to do. But in the process of doing that, you're going to go, wait a minute, I have a leaving group problem here. Well, think about how the aluminum might participate, and I will leave that for you as a mechanism to think about. One more case of this. What about an amide? Actually, in this case, we don't even need the H3O+. What will an amide do? Now, if you're doing what I've asked you to do up to this, bless you. If you're doing what I've asked you to do up to this point, you're going, aha, patterns. Lithium aluminum hydride converts a ketone into an alcohol, an ester into 2 alcohols, a carboxylate into an alcohol. So lithium aluminum hydride should convert an amide into an alcohol. Thanks for playing. It's really good thought to think that, but it turns out, because of the way aluminum interacts with the O- intermediate, that in fact the oxygen, not the nitrogen, becomes the leaving group, and the product we get here is an amine where the carbonyl has been, both bonds of the carbonyl have been replaced by hydrogens from the ALH4 minus. Now, you're not responsible for working out either. You're not responsible for these mechanisms, but you should probably be able to puzzle them out for yourself, especially when you know what the product of this one is. You should be able to look at that and go, wait a minute, at what point does the mechanism do something a little bit different that gets me up here? So lithium aluminum hydride will attack any of the carbonyl-containing functional groups. We haven't talked about acid chlorides and anhydrides and that sort of thing, but the mechanisms are pretty much the same kind of thing. All right, one last related to carbonyl addition and substitutions I'm going to talk about before we shift to talking about enolates. And that is, as I promised, if you were good, have you earned it? Have you been good? Bree, have they been coming to discussion section in office hours? So they've earned the treat? Okay, Bree says okay. So let's talk about Chi-Chi Bobbin. Yay. The reason we're going to talk about the Chi-Chi Bobbin reaction here is partly because this is the hydride leaving case, but also because I want you to think about the parallels between the Chi-Chi Bobbin reaction and the carbonyl chemistry we've talked about. The Chi-Chi Bobbin reaction doesn't have carbonyls in it. There's no carbonyls anywhere. As a matter of fact, here's what the Chi-Chi Bobbin reaction is. If we take pyridine, that's like benzene, except we've replaced one of the carbons, the CHs with a nitrogen. We can react that with NaNH2. Often we use ammonia, liquid ammonia, as the solvent for this reaction. And what happens is that a hydrogen on the carbon next door to the nitrogen gets replaced. Now, in terms of mechanisms, if you look at this, you'd say the only possibility that we know that's anywhere close to this is electrophilic aromatic substitution. Pyridine's aromatic, and I'm replacing one of the hydrogens on the ring. These are not electrophiles. So this is not electrophilic aromatic substitution. In fact, it looks like the NH2, remember this is Na plus NH2 minus, it looks like the NH2 minus is actually doing something to the pyridine. And so here's NH2 minus, it's forming a bond to that carbon, NH2 minus, well, it has a negative charge, so it must be a nucleophile. So let's think about maybe that as a possible way to begin the mechanism. Why would NH2 minus want to attack this bond, which we have drawn as a nitrogen-carbon double bond? Does that look familiar to anything, parallel to anything we've been talking about? Yeah, why is a CO double bond a carbonyl? Why is a carbonyl an electrophile? Because there's a difference in electronegativity between oxygen and carbon. In a carbonyl, we have delta minus delta plus, because oxygen is more electronegative than carbon. We make the same argument here. We have a delta minus delta plus, a polarized pi bond, because nitrogen's more electronegative than oxygen, or nitrogen's more electronegative than carbon, and because it's a polar pi bond, it is susceptible to nucleophilic attack. Now, not as easy to do nucleophilic attack here because, number one, the delta plus isn't as big. Nitrogen's not as electronegative as oxygen. And number two, when I draw the intermediate for this step, let me draw it over here just so I have some space. So there's the intermediate that comes from the nucleophilic attack. I've taken the pi electrons and given them to the nitrogen. I'm paying another price to go from pyridine to this intermediate. What's that? Aromaticity. So this is also much more expensive to do than just adding to a carbonyl. But we can still do it, partly because once I've made this negative charge, not only is it an electronegative atom nitrogen, but I have nice resonance delocalization as well. So that's the reason this can occur. But it's not done, because it still has a negative charge on the nitrogen. It would still like to get rid of that negative charge on the nitrogen. What do you think it does first? Let's see. Tetrahedral intermediate, negative charge on the oxygen. This is kind of like a tetrahedral intermediate. I took an sp2 carbon. It's now sp3. With a negative charge on that electronegative atom, what do you think we should try to do first? eject a leaving group. See, there's those patterns again. You didn't even know they applied. All right, eject a leaving group. Use the nitrogen lone pair to come back here. Now, there's an additional advantage, by the way, to eject a leaving group here. What do you think that is before we discuss what the leaving group is? Restores aromaticity. I get my pi bond back. Now, what's my leaving group? Well, I mean, that finishes the mechanism. So it looks like what's leaving is it's losing the H, the hydride ion. That's going away. The hydride ion is the leaving group. Normally, we would say, no, can't do that. Because our rule is that hydride ion is not a leaving group except in the Chichi-Bobbin reaction. Well, just because we've called it the Chichi-Bobbin reaction, named after a person, Chichi-Bobbin, I kid you not, the reason it leaves here, why does it leave here? Hydride normally allows a leaving group. But why does it leave? Well, that's not the best place to put a negative charge. This is like you currently live in the apartment called carbon-hydrogen bond, and now you're going to move into another apartment called hydrogen. How big is that new apartment you're moving into? This is worse than living in a refrigerator box under the freeway. This is like living in a toaster box under the freeway. Look up there in the periodic table and tell me what atom has a smaller atomic radius than that. There ain't none. This is it. This is as tiny as you get. And the electronegativity of hydrogen isn't very good either. And there's no resonance to stabilize that. Oh, and it leaves with a negative charge. And there's no inductive effect to help it either. It's about the most awful leaving group you could think of. But it does leave. What helps it? The restoration of the aromaticity. That helps it. That helps lower the energy of the transition state and make this possible. So what happens in the Chichi-Bobbin is we replace the CH bond with the CN bond. It's actually what we call nucleophilic aromatic substitution because it's substitution on the aromatic ring using a nucleophile. But the main point I want to make here in this is that it looks very much like a carbonyl substitution kind of reaction. It's different because of the leaving group. It's different because of the aromatic ring, but it's still nucleophilic attack with substitution on a polarized pi bond. All right, so at this point, we're going to shift over to our lecture supplement and talk about enolates. Watch your toes. So we're going to be on page 57. Is that good for you? More lights down? That's good? All right. Now, we're going to talk in our second to last lecture topic here, which we're going to talk about today and Friday and maybe a few minutes into Monday. We're going to talk about three related, you could call them functional groups. They are all cases where we have a carbon-carbon pi bond with either an oxygen or a nitrogen attached to that pi bond. The presence of that oxygen or nitrogen makes the pi bond nucleophilic. And because we have a nucleophilic carbon, it ends up being a reasonably useful way to make new carbon-carbon bonds. In addition to the topics we're going to talk about at the end here, enols and enamines show up frequently in biology, biological structures as well. All right, so let's start with an enolate. That's the carbon-carbon double bond with an O minus attached to it. We can draw a resonance contributor, which puts the negative charge out here on the carbon, and there is our hybrid with a delta minus on the oxygen, delta minus on the oxygen on the end. We can talk about enols. We did talk about enols way back when, in maybe a third of the way through this course when we were talking about addition to carbon-carbon pi bonds. We talked about hydration of an alkyne. Remember keto-enol tautomers? We'll talk a little bit more about that in this topic. But an enol is like an alkene with an alcohol on it. That's why we call it enol. And it has resonance, although its resonance is not as important as it is for the enolate. It still gives us a resonance contributor which has the delta minus out here on this beta carbon. Enamines are alkenes with amines attached, hence their name enamine. And they also have that same kind of resonance, which puts the negative charge out here on that beta carbon. So all three of these structures, whether it's oxygen or nitrogen that's providing the electron density, put some extra electron density out here on the end, and that suggests they have nucleophilicity, and that turns out to be the most important thing we're going to talk about with these guys. There are other things they can do, but we're going to talk mostly about them in terms of nucleophilicity. Now let's start with the enolates, because we're going to spend most of our time here talking about enolates. And let's start by talking about how do we make an enolate. Well, one of the ways to make an enolate was by, the most important way by far, is by one of the carbonyl mechanism fates that we'd previously mentioned, but really haven't done anything with. Remember our carbonyl fates were except nucleophilic carbon. Have we done any of that? Lots. That's a good summary. Except electrophile, usually proton and oxygen. Have we done any of that? We've done lots of that too. So here is form enolate, which we've mentioned before, but now we're actually going to use it. Form enolate is, use a base to take the proton away from the carbon next door to the carbonyl. We often call that the alpha carbon. Remember alpha and beta when we talked about elimination? This is the alpha carbon because it's the carbon that's directly attached to the functional group of interest, the carbonyl. It has nothing to do with it being the dominant carbon. It doesn't run around in the molecule with a big silver streak on its back and beat its chest and, be the first to mate with the female carbons in the molecule. It's not that kind of alpha carbon. Thank you. I'm glad you appreciated it. If you haven't taken any behavioral biology, ask your friends who have. They'll tell you about alpha males and gorillas and all that other kind of stuff. Anyways, all right, so we take that proton away. It puts the negative charge on the carbon. Of course, we have lone pairs next to the carbonyl, lone pairs next to pi bond. Very standard resonance. We've seen this many times. Lone pairs and pi bonds switch places, so we now have a new CC pi bond and an O minus. These two resonance contributors taken together we call the enolates. And when we refer to the enolate, we might be talking about one of these, both of these, the resonance hybrid. Doesn't really matter. They're all the same thing. Now, taking away the proton is an issue we need to talk about because, number one, there are different carbonyl-containing functional groups, aldehydes, ketones, esters, carboxylic acids, etc. And the nature of the carbonyl-containing functional group will influence how easy or difficult it is to take that proton away, i.e. how acidic that proton is. So that's something we need to address. We also need to address what kind of base do we use to take that proton away, because as we're going to discover, there's an issue of with basicity here. And we're also going to talk a little bit about the position of the equilibrium, i.e. how much enolate is formed. That also turns out to be important because it will help us understand the way why some enolate reactions go one way, but other enolate reactions do something different. All right, so let's ask the first question, or answer the first question. How does carbonyl functional group's structure influence the acidity? We're going to talk about pKa here. Now, pKa, remember, is our how we quantify acidity. Lower pKa means more acidic. And if you don't remember that, think of sulfuric acid, whose pKa is about -5 or -7 or -9 or -10. But it's minus a lot depending upon how you measure it and which textbook is listing it. But negative a lot means strong acid. Methane, terrible acid, pKa 50. Water's pKa is 15.7. Water, not a terribly strong acid last time I checked, but just let me review that fact. Yet no burning sensation, so thank you. I'm glad you got it. All right, so let's talk about this now. When we want to think about this in terms of the acidity, there's a lot of ways to do it, but a good way to do it is to think about it in terms of the conjugate base stability. In other words, the more stable we make the conjugate base, the easier the conjugate base is to form, and the more eager, therefore, the corresponding acid is to give up its proton. So to wrap your mind around that, think about a carboxylic acid. A carboxylic acid is called a carboxylic acid because it likes to give away its proton. Why does it like to give away its proton? Because in going from carboxylic acid to the carboxylate, its resonance circumstance improves. It gains more resonance stabilization. It wants to do that, right? Resonance is like money. It wants to keep it. If it doesn't have it, it wants to get it. So carboxylic acids like to give away their proton because the conjugate base is pretty stable. All right, so we also need to remember that in equilibrium, in terms of an acid-base equilibrium, favors the more stable side. And in terms of acids and bases, that means the side of the equilibrium which has the weakest acid and the weakest base. That means on one side of the equilibrium, you have weakest acid and weakest base. On the other side of the equilibrium, the strongest acid and strongest base. And if you haven't written the equilibrium where the two weakest are on one side and the two strongest are on the other side, you've written something that doesn't happen that way. And you can write whatever you like, but the weakest will be on one side and the strongest on the other. Now, you may find it useful to review your acid and base reading. The OCATSA chapter for that's available if you need to review that. Look at tutorials on the website. Look at your 14C notes, a whole slew of places where we've talked about structural features that influence basicity. All right, let's start with a very simple, very common case. That's ketone. Here's a ketone. Ketones turn out to have a pKa of 19. What that means, since the pKa of water is 15.7, so that is the pKa of 19 is higher, more positive than 15.7. That means that acetone, this ketone, is a weaker acid than water. And consequently, this equilibrium, since it favors the weakest acid and base side, lies to the left, the way it's written. Now, if you start with approximately equal concentrations of reactants, you can actually estimate what the equilibrium constant is by simply taking the difference in pKa values. The OCATSA acid-base chapter rationalizes why you can do that, but this equilibrium constant is essentially 10 to the minus 3.3 lying towards the left. Okay, that's fine. By the way, I don't expect you to memorize pKa values, but if you know them, it can be useful. Why should acetone be less acidic than water? Now, here's one of those cases where you go, wait a minute, there must be a typo here, because the conjugate base of water, which is hydroxide, has no resonance stabilization for its O-, whereas the enolate form from acetone does have resonance stabilization. So shouldn't the enolate of acetone be happier than hydroxide ion? And this is one of those cases where resonance, turns out, doesn't quite play the role that we would expect. Now, this is important because this shows up in a lot of carbonyl compounds. All these enolates have resonance stabilization, some more than others, but the resonance doesn't carry the weight that we would expect relative to hydroxide. I can give you a more sophisticated explanation if you'd like. Come and ask me sometime, or read the enolate section of the OCATSA, which is just actually going to become available shortly. If you want access, send me an email. I'll tell you how to get there. But that may explain some of that for you. But anyways, deprotonating ketone with hydroxide only gives a little bit of enolate. Now, here's another issue I want to address. Only a little bit of enolate. This means that if I take acetone and I chuck in hydroxide and I let that come to equilibrium, only about 1 in 4,000 or so, whatever 10 to the 3.3 is, only 1 in about 4,000 acetone molecules at equilibrium is its enolate. Everything else remains as acetone. So that means when I form that enolate, it's swimming around in a sea of acetone. So something to think about. That will be an issue later when we talk about what enolates do. All right, let's look at some other functional group issues with pK. Now, we're not going to talk about all of them. We really only need to talk about 2 structural differences. A number of them you already know. You know about how conjugation works. You know about how inductive effects work, that kind of thing. We don't need to talk about those in particular. But we will talk about having an extra carbonyl. So imagine we have 2 carbonyls that are separated by 1 carbon. And if we use a base to take away the proton between the 2 carbons, there's our enolate. And now that enolate with its lone pair on the carbon actually has 2 additional resonance contributors, not 1 but 2, because we can take that negative charge and give it to either of the carbonyl oxygen. So I can give it to the carbonyl oxygen on the left, or I can give it to the carbonyl oxygen on the right. And if you don't see that, I encourage you to draw out the lone pairs and the curved arrows and see where that comes from. Now, because this negative charge is delocalized compared to the acetone case we had on the previous page. Here, the negative charge of the enolate is spread out over 3 atoms. 2 oxygens, 1 carbon. In the acetone case, it was only over 2 atoms, 1 oxygen, 1 carbon. What happens to relative stability, everything else being equal, when you take that negative charge, those extra electrons, and spread them out over even more atoms? I'll give you a metaphor to think about it. Imagine you live in a house, you and your friend. Right? You're the lone pair of twins. You look exactly like your friend. You're kind of little. You have a negative charge. right? You like to obey quantum mechanics. You're an electron. You're in that house with your friends. You're going to move into a new house, right? Because you used to be part of the CH bond fraternity or sorority or whatever it is, club, and it broke apart. So they kicked you out. Now you're looking for a new house to live in. Do you want to live in the house that has 2 rooms or 3 rooms? 3 rooms, right? More space to run around in. Same thing with little kids, right? Remember little kids, the more space you give them to run around and they go la 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 la, they're happier. Same thing here. You give those electrons more space to spread around in, the happier they are. What happens to the ease of removing the proton when the conjugate base, again compared to acetone, when the conjugate base is more stable? Is it easier or harder to take the proton away from this pentane dione? It's easier because the conjugate base is more stable. As a matter of fact, that's exactly what it says here. More extensive delocalized. There's also conjugation that helps as well. And so that makes more stable conjugate base, therefore, compared to acetone, lower pKa. Adding the second carbonyl drops the pKa by about 10 pKa units. So this proton between the 2 carbonyls, pKa about 9. Now if we use methoxide as the base, methanol has a pKa of 15.5, very similar to water, and we expect that. HOH versus HOCH3, very similar structures, very similar acidity. So in this particular case, we now have pKa 9, 15.5. Which of those is the weaker acid, the pentane dione or the methanol? Methanol is the weaker acid. It's the higher pKa. So this time the equilibrium lies to the right by about 10 to the 6.5, so that's like 4 or 5 million, something like that. So what that means is if I take pentane dione and add an approximately equal amount of methoxide, CH3O-, only about 1 in a million of the molecules remains in the acid form. The vast majority, virtually all of them, excuse me, are converted to the enolate. So more stabilization, more formation of enolate. Now, what about an ester case? Here's an ester. I can do the deprotonation very much in the same way I did with the ketone. Take away the alpha hydrogen, get my resonance contributors, the enolate resonance contributors. Those look fine. Looks very much like the ketone case. But there's an additional resonance contributor that has to be considered. Can't be ignored. Has to be considered. The additional resonance contributor comes from the fact that we have a carbon-carbon double bond. We have a pi bond with lone pairs next door. What happens when you have lone pairs next to a pi bond? Switch resonance, right? They switch places. Exactly like we did here. Lone pair and pi bond switch places. So lone pair and pi bond switch places. We end up with a third resonance contributor. Now, a lot of times when it comes to resonance contributors, we can say, okay, I can draw that, but is it important? How much does it matter? Let's make that analysis. This third contributor we've drawn relative to the first 2 has what badness? This is not as significant as the first 2 we've drawn. The first 2, this has something that makes it less significant. It is avoidable formal charges. Not just formal charges. The enolate has, these 2 first structures have formal charge that's unavoidable because of the number of electrons that are there. You have no choice. But this third structure has 2 more atoms that have formal charges. Here we only have 1 negative charge. Here we have 2 negative and 1 positive. That's the only issue it has, though. So it's a little bit worse resonance contributor, but it only violates one of our preference rules. So it's not as important, but we can't ignore it. It's like, how many of you have like a little brother, right? Unimportant, but can't be ignored. And sometimes, like this little resonance contributor, they make your life less happy, right? Right? Maybe that's a metaphor I just thought up, and let's see how well it works. The reason, all right, so we have to consider this contributor. Now, when we construct the hybrid, what this tells us is, our hybrid looks like this now, and of course we have a delta minus on the carbonyl oxygen, a delta plus on the OCH3 oxygen from this contributor, and a delta minus out here on the alpha carbon. And it looks kind of like the ketone enolate, except the resonance stabilization comes from spreading electron density out. The OCH3 oxygen is working against that. It's saying, pi bond, you're trying to spread electron density out, I'm going to give you more electron density. Here's a metaphor. This one I didn't make up just this second. I made this one up actually a couple of years ago. And it works, I think. One of my tasks at the house, so I feed the cats in the morning, so I got to clean up after them in the afternoon. That's one of my jobs, clean the cat box. There are times when I'm cleaning the cat box, and Mama Cat, big Mama Cat, is sitting there watching me, making sure I'm trying to do a good job. Whatever. She's the quality control inspector. I don't know. But there are times when I'm sitting there cleaning out the, cat end product, that she comes right up and plops herself in the box and squats down and makes herself comfortable and proceeds to do her business while I'm trying to clean a cat box. Any of you have a fur people? Or a cat box trained dog? Dogs will do this too, right? The point is, you're trying to clean the cat box, and here's the cat working against your efforts. It doesn't help the circumstance. It makes you a little crazy. Makes me a little crazy, that's what it does. So what's happening here is the OCH3 oxygen, it's taking those lone pairs and pushing them into the portion of the molecule where we're trying to get electron density spread out. It doesn't help things. If you add more electron density to the enolate, remember resonance stabilization comes from spreading it out. If you add more electron density to the enolate, what does it do to the enolate stability? Does it help it or hurt it? It hurts it. And when you make the enolate less stable, what does that do to the conjugate acids, the things with a proton already on it? What does that do to the desire of that molecule to give up its proton? It says, I don't know, if you take a proton away, my enolate is less stable. The less stable enolate, less acidic carbonyl. So the net effect is that esters are less acidic than ketones because of this electron donation out here. Here, this is an unusual case, but we've seen examples of this before, of cases where instead of resonance taking electron density away, it's importing it. All right, so an ester has a pK of about 25, and if we react that with methoxide, the same base we used up here, now the equilibrium, there's our ester enolate, the equilibrium lies to the left by, the equilibrium constant is 10 to the minus 9.5. That means that if I take an ester and roughly an equal amount of methoxide and mix them together, only about 1 in maybe 4 billion of the ester molecules are converted to enolate. So there's very, very, very little enolate. Put that in perspective. Imagine every person in the world was a molecule of ester. And we collided with another planet called sodium methoxide, and so all the sodium, or the aliens invade. There's 6 billion sodium methoxide aliens come down to Earth. Only one of us gets deprotonated. Only one of us gets taken away in the spaceship and goes to planet enolate. No? All right, I won't use that one in the future then. Maybe if you guys wrote metaphors for me, would that work? Extra credit? I'm not sure I want to read some of the metaphors, I'll tell you. Because then I'm going to get metaphors about hitting my ex-wife and cat box and, all sorts of other things. Maybe I will do that, though. I'll have to think about that. All right, so the amount of enolate that's formed is going to be a function of the nature of the carbonyl, its pKa, also what the base is as well. But you may have noticed, let's go back to this ester case for a second. You may have looked at this and said, wait a minute. If I take an ester and react it with CH3O-, we're having the proton taken away. I get that. That makes the enolate. But in addition to being a base, methoxide can also be a nucleophile, right? So this kind of thing can be happening. Are those competing? Yes, they are. We gotta discuss that issue because that could be a problem. If we're trying to make enolates, can we just ignore the substitution issue? Sometimes yes, sometimes not. So let's talk about that. So here in our ester case, now I'm going to use hydroxide here instead of methoxide because hydroxide will make this problem even more obvious. There is a competition between hydroxide functioning as a base and making an enolate, and hydroxide functioning as a nucleophile and making the tetrahedral addict. And once there's a tetrahedral addict with a negative charge, we can eject a leaving group, and that would ultimately lead to substitution in this case. So how are we going to pick between these? Well, we have a general rule, which we've used several times, that says proton transfer is generally faster than acid-base reaction. So we're saying that enolate formation is going to be faster than the nucleophilic attack. But In a lot of these cases, the amount of enolate that's formed is very little. So in the ester plus hydroxide case, for example, which is the same as the ester plus methoxide case, only a teeny, teeny, tiny amount of enolate is formed. There's still plenty of ester left over to do nucleophilic attacks. So simply invoking the fact that enolate formation is faster, that's not going to get you over this problem. Now, even if that wasn't an issue, even if you had a really, really strong base, you could still get addition competing as well. How do we get around that? Well, we can't say, let's just make the nucleophile really, really strong, and maybe that'll help it compete. Because as nucleophilicity increases, maybe you've noticed this in this course, as nucleophilicity increases, basicity tends to increase as well. Water, not a great nucleophile, not a great base. Hydroxide, good nucleophile, good base. NaNH2-, the one we talked about up here in the Chi-Chi-Bobbin reaction, really good base. Also a good nucleophile, but as nucleophilicity increases, you tend to have things behave more like bases than nucleophiles. So NaNH2 actually usually behaves more like a base than a nucleophile if it has a choice. All right, so the nucleophilicity issue, we can't get around that really too easily. But we can take advantage of a steric hindrance issue. Because if you think about this addition versus substitution, or addition versus deprotonation, here's a ketone. The base has a choice of taking the proton away or attacking the carbonyl. And generally speaking, these protons are less sterically hindered, easier to approach than the carbonyl carbon. Build a model, convince yourself of that. So how can we take advantage of that? We can take advantage of that by remembering that a strong base is still a strong base, but if we make it sterically hindered, we can reduce, inhibit, make it harder to attack the carbonyl because it's sterically hindered. Give it a greater preference, if you will, to go for the less sterically hindered hydrogens. Now, all sorts of bases that do this have been developed. There are literally dozens of them. But the one which works the best, which is the most common, is this guy. It's called lithium diisopropyl amide, often abbreviated LDA. It's a nitrogen with a negative charge, so two lone pairs and a negative charge. It has two isopropyl groups, so these big isopropyl groups whizzing away out here. That's where your steric hindrance comes from. And it usually is the lithium cation. This is a very strong base. It favors equilibrium formation, enolate formation over nucleophilic attack. So in other words, if I take an ester, react it with LDA, so I'm abbreviating it as the isopropyl groups is IPR. That's IPR isopropyl. So we have a nitrogen with two isopropyls, taking the hydrogen, making the enolate. There's our enolate. There's our dimethylamine, our diisopropylamine out of that. So number one, because it is so sterically hindered, we get virtually no addition. Number two, something else that also is useful to know here is because LDA is such a strong base. This pKa, by the way, belongs to this guy, not the enolate. Because this pKa difference is 11, that means the equilibrium lies to the right. Equilibrium constant of 10 to the 11th. How much is that? That's 100 billion. That means, if we go back to the aliens invading the Earth example, if 100 billion people lived on the Earth, I think we're going to be there in about 3 years. If 100 billion people lived on the Earth and the spaceship enolate landed and it had 100 billion enolates on it, the spaceship LDA landed, it had 100 billion aliens on it, every single one of us would be deprotonated. Everything gets converted to the enolate. Unlike the case we talked about before, which was only 1 in 6 billion, this is everybody gets converted. So complete conversion to the enolate. Now, I do want to point out something else, by the way, since we're here. The abbreviation for this molecule is LDA. LDA is a base. Occasionally on an exam, somebody writes LSD. Now, that's a completely different molecule, but I should point out that LSD is acid, not base, for those of you who are... So if you want to protonate something, use LSD. And just a safety issue while we're at it, if you're taking LSD, and drinking, sometimes when you take a pill, you drink water afterwards, right? Remember, when you do that, you put the LSD into the water. You don't pour water on top of the LSD because it's always acid into water, not water on top of the acid. Just reminding you of that. How many of you remember LSD? It's not as popular as it used to be. No? How many of you remember the 60s? How many? You weren't even born in the 60s, right? They say if you remember the 60s, you weren't truly in the 60s. But all seriousness, though, if you want to mess around with drugs, it's your body. You can do what you want with it. LSD is one of the ones you don't want to mess with. I have a friend who lives on the East Coast who, as an undergraduate, 1978, took one hit of LSD, 50 micrograms. Last time I talked to him, granted this was a couple of years ago, but he was telling me he still has flashbacks. And these are not pleasant flashbacks. He's driving down I-95. He works somewhere in Connecticut. He's driving down I-95 going home, and things begin to melt when you're driving. Not very pleasant, so don't mess with that drug. All right. One last thought to think about today. All right, we talked about making an enolate, so what big deal, who cares? What do we do with it? The fact that the enolate has negative charge, whether it's on oxygen or carbon or shared if you draw the resonance contributor or the resonance hybrid, the fact that it has a negative charge suggests that it's a nucleophile. And it turns out enolates, generally speaking, are pretty good nucleophiles despite their resonance delocalization. They're pretty good nucleophiles. So what could we do with them? Well, so we react them with electrophiles. Now, it turns out that some of the most common electrophiles we react them with are electrophiles that are based on carbon. But the issue is the enolate, because it has some contributors where we have negative charge on carbon versus some where we have negative charge on oxygen, potentially that could lead to two different products. If we use the contributor where the negative charge is on the carbon, we would form the new bond, whatever, to the electrophile, whatever it is, out here. So there's our new bond. We formed a new bond between the alpha carbon, and we now have our carbonyl left over. On the other hand, if we use the O- contributor to form the bond, we now have a carbon-carbon double bond with O, whatever the new thing is, new bond up here, though. Very different structures. Which one of these is the major pathway? Well, we might argue that reaction at oxygen is the major pathway because the oxyanionic contributor, that's the major contributor. That's more stable. The negative charge is on the more electronegative atom. So there's more charge on the oxygen. So this should be the major pathway. As it turns out, for reasons that are above what we're going to talk about here, Mother Nature has decreed for the kind of electrophiles that we're going to react with enolates, the reaction actually occurs at the carbon. So even though this is the minor contributor, this is the major pathway. Now that's good because it's a great way to make carbon-carbon bonds. Enolates are stellar for doing this. There are big fat books that basically say, here's ways you can use enolates to make new carbon-carbon bonds. Even though we draw this as the O- is the major contributor, it still forms the carbon-carbon bond. All right, so next time when we come back, we will start talking about enolates as nucleophiles and reactions, so you might want to look ahead, start thinking about alkyl halides. That's where we will pick up on Friday.